I'd like to thank the organizers for inviting me to speak here. It's always great to be back in London. What I want to do in this talk is not give you a lot of technical details of any specific problem, but I want to talk about this sort of narrative of fine-tuning in quantum theory that's emerged over the past few years, and why I think it's a major problem that we should worry about. So I will throw in a few technical results here and there during the talk, but I want to concentrate mainly on the concepts. So because we're here celebrating the centenary of David Bohm, I thought I'd start by saying one thing which I think is really important about David Bohm's work in the 1952 papers was that really it was the beginning of what I think is a revolution in physics, which is to take quantum theory seriously as a fundamental theory of the entire universe with no need for the quantum classical split as you have in Copenhagen. So really without this step, the whole concept of things like quantum cosmology or even quantum computing, because if you have a universe with a quantum classical split, it's very natural to think that information, which is a human concept, goes on the classical side. Only when you're thinking of quantum theory as a theory of the entire universe would you come up with the idea that, hey, even computers obey quantum mechanics. So 1952 was really the start of a revolution in quantum physics, which was an extremely slow burn revolution because, of course, these ideas weren't taken seriously for a long time. But whether or not you think that Bohm's specific approach is the right one, this was, I think, a very significant change in attitude to quantum theory. Okay, so the outline is 3 questions. What's the problem? How bad is it? And what can we do about it? Okay, so I'm going to try and address all those 3. So first of all, what's the problem? I want to acknowledge here that I have a certain intellectual debt in this. The ideas that I'm presenting here originate, well, primarily with Rob Speckens, but this pointer isn't working. Oh, okay. Primarily with Rob Speckens, but Anthony Valentini was very influential in our thinking about how to understand Bell's theorem. I'm not trying to suggest that he was the first person to think about it this way, but that's where I get the ideas from. So what I want to talk about is really a bit of a refinement, slight generalization of something due to Rob Speckens. Now, implicitly in this discussions of fine-tuning, there is an implicit assumption in it, which I think is very rarely explicitly stated, but I think it helps to make clear why we worry about this. So I'm going to try and wear my heart on my sleeve and make this assumption explicit. I think something like this is an article of faith of most theoretical physicists, especially if you work on a theory that's kind of speculative. The brief slogan is, if it ain't impossible, then it happens. But in more detail, what I mean is that if you have some phenomena that occurs in a solution to the equations of the laws of physics, then either we expect it to occur naturally somewhere in the universe, and you expect to be able to find observational evidence for that. Now, that observational evidence might be rather indirect. I can't directly see the interior of a black hole, for example, but I can infer properties of it from what I see, and based on the fact that general relativity is otherwise well confirmed. So I don't necessarily mean directly seeing something, but gathering evidence for it. Some solutions to the laws of physics just don't represent things that naturally occur, but we're very clever, and we can often engineer systems in which it occurs. For example, large vitamin molecules do not commonly interfere on their own, but as Marcus told us, we can engineer systems in which that happens. Now, if you think about the notion of a quantum computer, literally, if we manage to build a scalable quantum computer, which is likely in the next few decades, I think, then you can pretty much have a quantum system evolve according to any physically reasonable Hamiltonian, right? So pretty much, if it's possible in quantum physics, you can do it on a quantum computer, right? Sorry?
How about entropy decrease?
Okay. Well, look, on a sufficiently small scale, I can make that happen by exploiting a supply of low entropy systems, right? So obviously, I can't make the entire universe, the entropy of the entire universe decrease, but I can simulate what that would look like in some sense. This isn't supposed to be, this principle is rather, I'm trying to flesh out this principle a little bit, but it's not, don't take it like 100% deadly seriously. It's just an idea that's behind, in some sense, the ideas I want to talk about. Sometimes you won't be able to directly engineer the system, but you might be able to engineer an analogous system. So for example, you may come up with some strange interference experiment which you propose for neutrons, and it might turn out that it's too difficult to do that, but we can do it with photons, and because we know the laws of physics, we regard that as sufficient evidence that the phenomena would actually occur. Okay, so I think, although I can't prove this principle, there's absolutely no way of proving this principle. It may be completely wrong. If you're working in theoretical physics, you have to have some kind of optimism that the effects that you're working on, if we work sufficiently hard, we'll find them somewhere. Okay, so now the other thing that's behind this idea of fine-tunings is really the Leibniz principle of the identity of indiscernibles. Or I should rather say that this principle motivates the idea. So the idea is that the Leibniz principle says that if two entities are alike in all their properties, then they really are the same thing. Okay? Again, it's not a principle I can prove. It's not true, not 100% true absolutely everywhere, but it has been a successful heuristic in physics multiple times. Just one example of that is basically Einstein's equivalence principle. The idea that you notice that gravitational and inertial mass always have the same value, and there's no real reason for that in Newtonian physics, so you invent a theory in which they absolutely have to be the same thing. Right? That's an example of the identity of indiscernibles being used in physics. There are many others that I could write down. Okay, so in quantum physics, we tend to use an operationalized version of a Leibniz principle. So note that Leibniz is vague here on what it means by properties, and you'll have different versions of the principle depending on what you call properties. We tend to use an operationalized version of Leibniz principle, and this is formulated by Rob Speckens in his notion of his generalization of the notion of non-contextuality. So this generalizes the notion that was used by Koshin and Specker. So the idea is that if I have two experimental procedures, for example, they might be state preparation devices, they might be measurement devices or anything. I have two experimental procedures, and they make the exact same predictions for any way that I can probe them whatsoever. Right? So, for example, I have two preparation devices. Any measurement device I put on them always gets me the exact same predictions. Okay, so then operationally they have the same properties, at least from the point of view of anything that you can observe. And then the Leibniz principle would imply that they should be the same thing in reality. That's the principle that's being used in Speckens' non-contextuality. So I want to slightly generalize that idea by saying that if the predictions of a theory obey some general principle, which might be, for example, a symmetry, rotational symmetry, for instance, then the theory of reality should obey that principle too. So suppose that from the point of view of every experiment I can do, then this thing I do in the lab looks like that thing except rotated by an angle theta. Then in my theory of reality, this thing should be that thing rotated by an angle theta. Right? This is just a generalization of that. Here, the symmetry would be the identity. Okay. So if this kind of principle doesn't hold, then we say the theory is fine-tuned. I want to explain why we use this terminology, because it can be a little controversial, and why it's a problem. But it will be helpful to introduce the first concrete example in order to do that. So I'm going to briefly look at an analysis of Bell's theorem, which is due to Wood and Speckens. Okay, so here's the setup, a theorist's version of the setup for a Bell experiment anyway. Okay, this is the natural causal structure written in the form of a Bayesian network or a causal network of a Bell experiment. So I'll tell you what these things mean. Here we have X and Y, those are the settings of our apparatus. A and B are the outcomes, and this is the hidden variable. And the arrows represent the possibility of a direct causal influence. Okay, so this is the natural causal structure that you would write down if you look at the locations of these things in space-time. Okay, so in the theory of causal networks, any network like this corresponds to a set of possible probability distributions. And here it is. Basically, you have for every variable, you have a factor that is conditioned only on its parents in the graph, and then you multiply all those factors together. And if you look at this condition for a while, if you take this thing and condition it on X and Y, you get exactly the Bell condition of local causality. Okay, so the natural causal structure, according to this kind of theory, is one that satisfies Bell local causality, but of course, this can't reproduce the quantum predictions. So we have to do something else. So you say, okay, well, I need a more general causal structure. Here are some examples of more general causal structures. This one here would violate what's called parameter independence. This one would violate outcome independence. This would involve some retrocausality, some influence from the settings onto the hidden variables. So in the causal modeling literature, there's a condition which is called no fine-tuning. This is where we take this terminology from, which says that so each of these causal structures, you can define the probability distributions that are allowed on them in terms of a set of conditional independences. And if you choose these parameters here in a generic way, then you won't have any other conditional independences in the probability other than the ones that are entailed by causal structure. So a generic choice of these parameters would lead to just those conditional independences. The no fine-tuning assumption is that the probabilities don't have conditional independences that are not entailed by their causal structure in this way. So obviously an individual experiment might have such things, but if we do a bunch of different Bell experiments with different settings and different state preparations and so forth, we would expect at some point to get distribution that's more or less generic in the parameter space that we're allowed. However, all the causal models that can reproduce the quantum predictions, such as this one or this one, for instance, are fine-tuned in this sense. Why are they fine-tuned? Because the no signaling condition is a conditional independence condition, and it's one that's not entailed by these graphs, because these graphs with arbitrary parameters will allow superluminal signaling. Okay, so that's the sense of fine-tuning that we mean for Bell's theorem. So another way of thinking about it is if we found that we lived in a world with superluminal signaling, we wouldn't have a big crisis in physics or anything like that. Well, it would be quite a big crisis, but we would simply conclude Einstein was wrong. Let's get on with physics in a non-relativistic fashion, right, if we saw that. But in this situation, it's a bit funny because, you know, what's funny about Bell's theorem is not that there's a superluminal influence, but it's that there's one that can't be used to send signals. That's the idea. So here's the general structure of a fine-tuning argument. We start by noticing that there's a property of the operational predictions of quantum theory. No signaling in this case, but it will be other things as well. Then you try to formulate a realist model. That realist model will have some set of free parameters in it that aren't constrained by the laws of physics or anything else. And then you notice that the operational property is only reproduced for very special choices of those parameters. Generically, it would be violated. And there's no law of physics that dictates that particular choice. Now, if you believe in the articles of faith, then that's a problem, because the articles of faith imply that if there's no law of physics, then we should find cases where it doesn't hold and be able to engineer them or observe them. and then you would expect to see a violation of the operational property somewhere. And then if you don't, that's a surprise. Okay, so that's the general format of the argument. So to talk about the other fine-tunings that I want to mention, I want to be a bit more formal and introduce a bit the ontological models framework in which most of these kinds of results are proved. So here we have, we're going to have a simple experimental setup where we have a preparation device, does some preparation P. Immediately afterwards, a measurement is done, a measurement M. In quantum theory, this preparation will correspond to some quantum state, a density operator, and the measurement will correspond to, in general, a POVM. But if you want to think about just orthonormal basis measurements, that will work fine for this analysis too. The measurement has some classical outcome, which is a random variable A in this case. Okay, so then quantum mechanics predicts that for this choice of preparation and measurement, there are some probabilities given by the Born rule. And now all we want to do is say that actually in the world, maybe the system has some physical properties that exist between preparation and measurement and that are responsible for this correlation. So we call that lambda, just as we do in Bell's theorem. And so now what happens is that when I make the choice of preparation P, some value of lambda is going to be selected with a certain probability, so there'll be a probability measure. And when I make the measurement, I'll have conditional probabilities for the different measurement outcomes, given what measurement I'm doing and lambda. So here's the example of a two-outcome measurement. So for every lambda, I have to have a probability of the two outcomes that sums to 1. And then if this model, then this model predicts that if I integrate those conditional probabilities over lambda with respect to this probability measure, then that's the prediction that the model makes. And of course, to be empirically adequate, these two probabilities should be the same, should reproduce the predictions of quantum mechanics. So that's the basic framework that we normally use. And you can consider Bell's theorem in this kind of framework as well. Okay, so now let me talk about Rob Spekken's notion of preparation contextuality. So first of all, we can come up with a notion of an operational equivalence between two preparations. What it means is that if for all measurements and outcomes of measurements, the probabilities are always identical, then we can't distinguish those preparations by any experiment that we can do. So examples of this would be two different ways of preparing the maximally mixed state in quantum theory, for example. So models called preparation non-contextual if whenever these are operationally equivalent, then they are represented by the same probability measure here in the underlying theory. So this really literally just is an instance of the operational Leibniz principle. It really is one instance of it. And so its failure will be a fine-tuning. So Spekken's, I'm not going to go through the details, showed that even a model of a qubit has to have the feature, cannot have this feature. So that's another fine-tuning. I want to talk about this. This is in a recent paper that I wrote with Matt Pusey. I'm not going to have time to go into full technical details, so I just want to give you a flavor of the result here. But it's to do with the notion of time symmetry in quantum theory. And in particular, this was supposed to be a generalization of an argument by Hugh Price, which I believe he's going to talk about a bit in his talk. So you may get some more intuition as to what's going on there. But for this, I'm going to extend the scenario a little bit. We still have a prepare and measure experiment, but I'm going to allow my preparation device to have an input, which is controlled by the experimenter, and an output, which is random, not under their control, and similarly for the measurement device. So now each preparation is going to be specified by a set of density operators, one for each possible input and output, and a set of POVMs indexed by the choice of measurement. The quantum probabilities will be, again, described by the Born rule. And now we're going to talk about the notion of an operational time reverse. So an experiment like this, we say, has an operational time reverse if there exists another experiment, different preparation and measurement, where okay, so these variables here, a prime and x prime, have the same possible values as b and y, and vice versa. And the probabilities are related in this way. So what this means is that if somebody gives you, runs one of these two experiments for many, many iterations and gives you a list which says, okay, this variable took the value A, this variable took the value B, et cetera, for each run of the experiment, then you wouldn't be able to tell the difference between this experiment running forwards in time and this experiment running backwards in time. So that's why we say there's a notion of time symmetry. It's different from some of the usual notions of time symmetry. So I'm trying to be explicit about what I mean. So we say that an experiment is non-signaling. So generally speaking, this kind of experiment, there can be a signal from the preparation to the measurement. It's happening forward in time. But some experiments happen to be non-signaling. You can make a non-signaling experiment if you want, which just means that you can't tell any information about the first input here just by looking at the output. Okay? So in quantum theory, this means that you have to set things up in such a way that the average density operator of the preparation, averaged over the outcomes of the preparation, doesn't depend on, sorry, I meant x here, doesn't depend on the input. Okay? Now, it's a fact that in quantum theory, every such non-signaling experiment has an operational time reverse. That fact is not true of every physical theory you could write down. It happens to be true of quantum theory. So this is a symmetry, and so you might say, okay, well, by the principle of no fine-tuning, if I have an operational time reverse, I ought to also have an ontological time reverse, where if I just include lambda, I get the same sort of thing happening. Okay, so that's roughly the idea. And then what we showed is that if you have an operationally time-symmetric theory that also has an ontological time-symmetric model, then the model has to obey the local causality condition. Again, now this is a time-like experiment, right? So despite the fact that these are time-like related, they still obey the Bell condition as you would write down for a space-like experiment. And of course, there are non-signaling experiments in time that violate Bell inequalities. You basically have to turn the CH-SH inequality settings on their side, and you get that. That doesn't happen in the classical probabilistic theory for non-signaling experiments, but it does happen in quantum theory. So that's another example of a fine-tuning. There's a symmetry, a time symmetry, which cannot exist at the ontological level. And so if you write down an ontological model with generic parameters, it won't satisfy the time symmetry. Okay, so how long do I have left, by the way? Where's Bob?
It's now 10 to 6, so you've got 10 minutes till your 10-minute course.
Oh, okay, good. Right, so now I want to talk a little bit about how bad is it. So we want to talk about how do you quantify a fine-tuning in general. So this is really an ongoing project, which is just beginning. There's a whole framework for talking about this. What I want to talk about today is just sort of a quick and dirty thing you can do for all fine-tunings kind of straightforwardly. So a crude way of doing it is to just say, okay, here's my set of operational predictions, and I can try to decompose it into a convex combination of some operational predictions that don't have the fine-tuning, right, that have a non-fine-tuned ontological model, and the rest, which could be fine-tuned. Then if you take the maximum possible value of p, then we'll call that the non-fine-tuned fraction, what percentage of the correlations that you're observing can be accounted for by a non-fine-tuned model, and the minimum of 1 minus p will then be the non-fine-tuned fraction. So the idea is that large values of p are good, small values of p bad, a lot of fine-tuning. So in the case of Bell's theorem, this particular way of measuring things, there are many ways of measuring non-locality that have been proposed. This particular way was studied in particular by Kolbeck and Renner in this paper. And they found that you could bound this based on a Bell inequality. You get this simple formula. So here, A is the algebraic maximum of the Bell inequality. Just make it as large as you can, only taking into account the fact that probabilities have to be between 0 and 1. C is the maximum value you can get with a local hidden variable model, and Q is whatever your observed quantum value of that inequality is. Now, there is a scenario, which I'm not going to go into details, called the chained Bell inequalities, which, when you take the limit of an arbitrary number of measurement settings, arbitrary large number of measurement settings allows you to make this thing go to 0. So in some sense, it's as bad as it could be from this point of view. There are other measures from which there are other measures which tell you different things, but at least from the point of view of this measure. One sort of funny thing about that is that because it's directly related to the degree of violation of the inequality, it gives you a sort of quick and dirty method for comparing experiments in some way, at least on some measure. So I just last night at about 3 a.m. tried to compute these things for the recent loophole 3 Bell tests. And I wasn't quite able to work my way all the way through the error analysis and give you error bars, but I can do that shortly. So at least for these two experiments, these are the values that you get. The third one, they used a kind of funny version of the inequality, so it was very difficult to extract the value. But since it's similar to this inequality used here, I expect this value to be more similar to this one. So normally, when we do Bell experiments to try and rule out local realism, we're thinking about them as hypothesis tests. Hypothesis, there's a local realistic theory. Let's try and rule out that hypothesis test. That is a hypothesis test. So as hypothesis tests, all of these experiments are absolutely fantastic. They rule out things to dozens and dozens of sigma, like much, they're fantastic hypothesis tests. Normally, when you test a hypothesis to that degree of stringency, you would move to trying to measure some parameters that are relevant in the effect. So the argument here is that we should try and compare the quality of these experiments now on some measure of non-locality that they imply. So this experiment is actually a much better hypothesis test than this one because they're able to collect much larger amount of data, and the error bars are really tiny. So as a hypothesis test, this rules out local realism much better than this one does. But as parameter estimation experiments, actually this is better basically because of the inequality that they used. And so this sort of, I think, suggests where we should be trying to go with these experiments. I should also say that getting lower values of p is somewhat closely related to the amount of work that you have to do to extract secret keys in a device-independent fashion. So low values of p are good for that purpose. Okay, so now let's move on to talking about preparation contextuality. For preparation contextuality, you can also get p equals 0 just by converting the chained Bell experiment. But there's a more interesting measure that we can compute, at least for some scenarios. And this measure is, again, I'm not going to go into details, but again, it's interesting because it's related to certain information processing tasks. Basically, suppose we have two preparations that are operationally equivalent, means their quantum predictions are exactly the same. They will, in principle, be represented by two different measures in the ontological model, and those measures will have some overlap region. So if we take basically the area of that region of overlap, this is just the measure theoretic definition of that, then that's a measure of the overlap. The reason this particular measure is interesting is because it's linearly related to the optimal probability of guessing which of the two preparations was made if you happen to be told lambda. So if it's p or p prime with 50/50 probability, one of those two is prepared, somehow you gain access to the full state of reality, then this is the optimal probability of guessing whether P or P prime was prepared. So if the scenario is sufficiently symmetric, and this is still a work in progress, by the way, with 2 graduate students. Eric Frieder is my graduate student at Chapman, and David Schmidt is one of Rob Specken's graduate students. One thing that we can say for certain right now is if we consider this kind of scenario, so what we're looking at here is 2 different ways of preparing the maximally mixed state. This is the equator of the Bloch sphere, so if we do a 50-50 mixture of these 2 states, or a 50-50 mixture of those 2 states, we get operationally equivalent preparations, and these are the measurements that we do. Our methods only work if there's a sufficient symmetry in the setup, so this is why we're using these things. For this particular scenario, we get this value for the overlap of those preparations. And you get the optimal case is where theta is pi upon 4, where you get this value. And actually, we know that that's tight because there exists an ontological model that has this particular, for a qubit which has this particular value. It's the model due to Koshin and Specker. So we know that that's the best you can do. We do have like a mathematical framework for generalizing this. Basically, we can take a set of operational equivalences and run an algorithm which will give us a bunch of inequalities, which we can then search through for good values. But I don't want to get into the details of that. Okay, so now at the end of the talk, I want to talk a little bit about what we should do about these fine-tunings. I think there are basically 3 strategies for dealing with them. One is just basically accept them. 2 is to explain them as emergent. It's good that we're at emergent quantum mechanics for that explanation. Or 3, we could look for a more exotic ontology which doesn't have them. Okay, so what about the first option? It's fairly obvious that there are many facts about our universe that aren't directly explained by the laws of physics. One such fact is that there's a person called Matthew Leifer talking to you right now. In principle, you could derive that from the laws of physics and the contingent initial state of the universe, contingent facts about our universe, but you would never expect a physics explanation of that, right? So there's certainly facts that are true that you wouldn't expect to have deep explanations in physics. So we could just accept a fine-tuned world in this sense. We could just accept that we live in a world with superluminal influences in which there's no superluminal signaling. That's just a contingent fact of the state of our universe, not a law of physics. That's just how it is. It's a possible explanation, and you're free to take it if you wish, but I think that if you subscribe to the articles of faith as I do, it's very strange if you're talking about a very general feature of the universe. Like, me standing here talking to you is one thing, but the fact that there's never anywhere in the universe any possibility to send a superluminal signal is a much more general fact, which would seem to be violated by generic choices of parameters. So it seems like it needs an explanation to me. Explain them as emergent. This is also a viable solution. So the classic example of this kind of emergence that I mean is just the relaxation of systems to thermal equilibrium. Right? So if you think about a generic state of n particles in Newtonian mechanics, you have 6 to the n parameters in phase space, but many systems that we see in the world happen to be in thermal states, and those are described by just a handful of parameters taking some values. So this is a fine-tuning in the sense that I've been talking about because there's vastly more possible states than there are thermal states. But we have an explanation. The dynamics drive systems towards these states when we look at them at a coarse-grained level, okay, for a generic initial state. So it turns out that this is actually a fact about the laws of physics. It didn't appear to be the way, together with a generic initial state, and that's what we want. However, if you subscribe to the articles of faith, 10 minutes. Okay, if you subscribe to the articles of faith, this implies you should expect to see some physical systems out of equilibrium, because it's possible, and hey, we do. Okay, so this is a good explanatory structure here. There's an apparent fine-tuning, but we can derive it, and furthermore, it doesn't always hold. That's exactly the structure you would expect from an emergence explanation. So this strategy in the case of de Broglie-Bohm theory was proposed by Bohm, and actually Anthony Valentini currently works on it, which is in Bohmian mechanics, the fine-tuning comes from the equilibrium hypothesis. Right? So if you start with a state in which the particles are distributed according to mod psi squared, that persists in time, and that's why we don't see superluminal signaling, for example, in Bohmian mechanics. But if we don't impose that hypothesis and just say there's some generic initial probability distribution of the universe, then there's supposed to be some thermalization-like process which would drive us towards this value. Okay, so that's the structure of explanation that's proposed as emergence. Now, the articles of faith, if you believe them, imply that just like in this case, we should expect to see some systems somewhere out of Bohmian equilibrium, and we haven't seen such things yet. Doing that would remove the fine-tunings, they wouldn't exist anymore, but now there would be explicit superluminal signaling. So you have to be willing to buy that somewhere in our universe, or somehow there's some superluminal signaling. I do expect this kind of explanation to play a role in explaining some of the fine-tunings, but probably not by this route, because I'm more inclined to think of Lorentz invariance as a fundamental symmetry. That seems to have been very productive in our understanding of physics. So this kind of explanation requires explicit violations, but I'm inclined to think that these are, at least Lorentz invariance is more of a fundamental symmetry. So I'm happy to explain some of the other fine-tunings in this sort of way, but probably not this one. Okay, so the third option is to say, well, all of this has been with respect to a particular framework for realist models, the ontological models framework. Okay? Break out of the framework, generalize it in some way, and suddenly you might find theories which don't have fine-tunings. So there's a couple of obvious ways to do that. You might have retrocausality in your theories. That's ruled out by the assumptions. Or the framework does assume that there's a single world, for instance. Okay? There are other possibilities that you might write down. These are at least two that I know how to handle. I don't have a lot of time, so I just want to say a few words. There is a project to try and formulate ontological models on a block universe. Again, it's closely related to things that Hugh Price and Ken Wharton are doing. And you can come up with a generalized notion of what you mean by Bell locality in that case. And it's not, as you might imagine, if you spent like just a couple of minutes thinking about retrocausality, you might think, oh, all hell breaks loose, you can have absolutely anything. There is still some constraint. You get, not going into the details, but you get a factorization condition that looks something like a Markov network, if you're familiar with what one of those is. Such a model can be Lorentz invariant in a sense and violate Bell inequalities. But since it allows retrocausality, in other words, the hidden variable state is not independent of the settings, you still have a fine-tuning. The fine-tuning is just to explain why there isn't any signaling backwards in time, given that that's allowed by generic parameters. I view that as more plausibly explained as emergent than the case of Lorentz invariance, but opinions may differ on that. Okay, I'm just going to finish here by saying that I'm not going to talk about this in detail, but I have been also worked on a bit on a many worlds kind of interpretation. It turns out that the Everett interpretation, although it doesn't have all of the fine-tunings I've talked about, still does have some of them. But we can try and get rid of that by adopting an even more sort of radical version of Everett that I've been thinking about. But since I'm close to out of time, I won't talk about that. So to conclude, I think the biggest obstacle for getting to the correct interpretation of quantum theory, as opposed to just one that works, is if we want to get useful explanations, then we need interpretations that aren't fine-tuned. Fine-tuning exhibits itself in multiple ways. So if you're thinking in this way, you know, a big deal is obviously always made about Bell's theorem, and that is a big deal. But there are other kinds of fine-tuning that we should think about that are in some sense also significant. And I think that probably the most promising directions involve breaking out of the ontological models framework, and then if there are still some fine-tunings left over, we explain those as emergent. But that's mostly work still to be done. Okay, thank you for your attention.